We're good? Good morning, everyone. Uh, we're going to continue our journey into relativity today, talking about general coordinates. But I wanted to say before I began that, uh, again, I welcome questions and interaction outside of class and this session. And to that end, I'm actually going to hold an office hour, if you like, uh, after lunch in the seminar room, which is just sort of across the hall here. Uh, and would really welcome any of you coming by to talk about any of the stuff that I'm presenting. And please know that I actually really enjoy doing that. That's a part of my job at Pomona College, to really be interactive with students, and that's what I really like about being at the kind of college that I am. So I am really take a lot of pleasure in being able to talk to anyone who would like to come by. So feel free. Don't be afraid at all. So last session we saw that general relativity tells us that gravitation is going to be involved with curvature in space-time. And we also saw last time how to construct tensor equations with, as long as we were in inertial reference frames and using Cartesian coordinates. But the trouble with curved space-time is that we can't use Cartesian coordinates all the time. And so we've got to figure out a way to deal with more flexible coordinate systems. And in particular, if you think about it, we're going to be writing equations ultimately that are going to determine the curvature of space-time. And since we don't know the curvature a priori, we better have a way of dealing with tensor equations that don't care at all what kind of coordinate system you're using. So this part of the class is really going to ultimately express the goal that we're going to try to be able to write physics equations that are completely disconnected from the eventual type of coordinate system that we use. And that will be a very powerful thing. Let's see what I've got. So I'm going to begin by defining what is called a coordinate basis, and this is a particular way of defining components in for a coordinate system, components of a vector or a tensor in a coordinate system. And then we'll see how we can generalize the ideas that we were working on last time to work with tensors in these coordinate bases. We're going to talk about how to do the gradient in a tensor way. Then we'll see from that how we can get the geodesic equation. And we'll look a little bit at geodesics in Schwarzschild space-time, which we talked a little bit about last time. One of my colleagues talked about that. And then I'm going to talk about lofts and lifts. Locally orthogonal frames and locally inertial frames, and which turn out to be very important ideas for connecting the abstract equations of general relativity to physical reality. So, all right, let's begin by talking about coordinate basis. Now, a coordinate system is really just an organized way for attaching numbers, coordinates, to points in space and time. The normal approach we've used in special relativity, we sort of imagine an orthogonal coordinate lattice, and we put clocks at every intersection of the coordinate lattice, and we synchronize all those clocks by sending light signals back and forth. That's all good and nice, but that doesn't work in general relativity. You try and set up those coordinate systems. They work locally, but not globally, and you begin to get you can't synchronize the clocks in a self-consistent way. There are lots and lots of problems. So we're going to talk about being able to assign coordinates in a completely arbitrary way. And the only assumptions that I'm going to make are two basic ideas. One is that space-time is not so pathologically curved that you can't take a really tiny patch of it and call it flat. Okay, that's one assumption. The other assumption, the only other assumption I'm really going to make is that our coordinate systems are smooth in the sense that nearby points in space and time have nearly the same coordinates. And I'm not going to particularly emphasize rigorous mathematics. In fact, quite the contrary. You might complain about my rigor here, but I really am going to go for intuitive, which I'm hoping you'll find more useful ultimately. So, the differential distance between 2 points in space, or 2 points in space-time, is the really frame-independent thing that we want to focus on. And so our job is ultimately to connect between our arbitrary coordinates and this physical displacement. I'm going to use as an example, imagine a sort of very strange and curvilinear coordinate system on top of a flat two-dimensional space. That's something we can draw. It's something we can imagine really easily. And if we can develop the tools for dealing with a coordinate system like this, that turns out that the tools work just fine in curved two-dimensional spaces or curved four-dimensional space-times. So the general process will be the same. So I imagine I've got a background here that's flat Cartesian two-dimensional space, and I've got some weird coordinate system which I'm just calling U and W coordinates. And you can see I've laid them out on top of this flat space. So we have a kind of a, we know because this is a flat space, we've got a Cartesian background, and the metric in that Cartesian background is just the flat space metric dx squared plus dy squared. It gives you ds squared. So we're going to think about how to do that though in this case. So in this coordinate system, whatever coordinate system I want to imagine here, I can set up basis vectors, one for the u coordinate and one for the w coordinate, and I'm going to define them this way. The u basis vector is tangent to a w equals constant curve, and it goes in the direction of increasing u. U is increasing this way, and e sub u is tangent to the w equal constant curve in the direction of increasing u. And similarly, I'm going to define an e sub w basis vector. It points tangent to a u equal constant curve in the direction of increasing w. And then I'm going to define that defines the directions of those basis vectors. But then I'm going to define the magnitude of those basis vectors so that the components of a displacement, a differential displacement, a really tiny displacement, is just the change in u times the basis vector. Can you see that that defines basically how long the basis vector is? And you could always make that definition. And similarly, the component of in the displacement in the w direction is just dw, so that we can write this kind of an expression. This is what we call a coordinate basis. And this only works for, even in flat space, really, it only works with weird coordinate systems like this if we're talking about a differential displacement. Because you can see that the directions of the basis vectors are going to change as you move from point to point. So if you go too far, your basis vectors are changing out from under you and you aren't getting an accurate representation. But if you zoom in on a differential displacement, the basis vectors are approximately straight. They're not varying much during that displacement. And you can really define what the displacement is by sort of adding these vectors the way I've shown it here. Now, really, technically what I'm doing, if I'm in a curved space or a curved space-time, I'm doing this addition on a tangent space that's touching the curved space at the point of interest here, the point P. And so if you want to think about it that way, but you can also just think about it. I mean, on the surface of the Earth, we draw city maps and we don't worry about the fact that the Earth is curved. A city is small enough that the discrepancies between the city map and the reality that it's trying to represent are so small that we can ignore them. And it's really the same kind of concept. Okay? So this is the way we're going to define a basis in an arbitrary coordinate system. And once we've defined such a basis, then you can define what I'm calling a 4-vector, but in this case, in our two-dimensional example, will be a 2-vector. But we're going to define the 4-vector's components to be the same kind of thing. You take the component is simply what you multiply times the basis vector in each case to get the vector. And so if you do that definition, then you're assured that when the basis vectors change around, if I do a coordinate transformation that changes the basis vectors around, then the 4-vector will transform just like the displacement vector. And that's the basic thing that we need. Okay? Now, how are we going to connect this to reality? So this is really pretty much sort of a kind of arbitrary abstract definitions. But we're going to be able to connect it to reality because the displacement vector, when you take its absolute square, that's a coordinate independent number. And so I'm going to take the definition of the way I'm defining the coordinate system in the coordinate basis. I'm going to multiply, do a dot product of that, and I simply want you to imagine the dot product in the two-dimensional background flat space, ordinary dot product. And what I've done is multiply it out there, and I get an expression that in index notation looks like this. And I'm going to define the metric tensor to be that set of dot products of the basis vector. And so then the metric tensor is linking these sort of arbitrary coordinates with the coordinate system independent number that represents the distance between the points in the space-time. We good with that so far? Yes. Where have I got it? Yeah, here. This. Yes, you're absolutely right. Good catch. Thank you. That's what I get for copying these LaTeX expressions. Okay, yes, thank you. What else? Anything else about that? Okay. So, We can really easily generalize this to four-dimensional space-time. In space, the only difference is that in space-time, the dot product of the time vector with itself, so if I have a basis vector in the time direction, the dot product of it with itself is a negative number. And actually, technically, there gets to be some complications if they're off diagonal components, but fundamentally, at least you have the possibility of having a negative number there. And and in flat space-time, you can always find a coordinate basis that where the basis vectors are all orthogonal and they all have unit magnitude, and it still obeys the idea that a displacement components are just the differential changes in the coordinate values. So you can do that in flat space-time. You can't do that in curved space-time. And that's basically the only difference. So this is a generalization of Cartesian coordinate systems that we're used to, but it's one that's way more flexible in terms of being able to deal with all kinds of coordinate systems. Yeah. Yeah. Uh-huh. Yeah. Yeah. Right. Yeah. Right. Uh-huh. Uh-huh. Yes. Yeah. That's right. That's right. And really, we're sort of imagining. I mean, you're highlighting the fact that, which is really important to get at, that all of these operations we're sort of imagining we're doing in the small patch of flat space-time that approximates the curved space-time in our local environment. And yes, you're totally right. All we're doing is deforming the coordinate system in that local area, taking the flat space coordinates and deforming them. But we all do it locally, so over a large region, the basis vectors vary in arbitrary ways and point in all sorts of strange directions and have strange magnitudes. So, and I want to also point out and make it very clear that when we worked in, say, we work in polar coordinates in a two-dimensional space, or spherical coordinates in three-dimensional space, they're curvilinear coordinate systems, but they aren't coordinate bases in the way that we're defining here. And this is something that actually took me a little while to figure out. So I'm emphasizing that for you. What's the difference? Well, in a coordinate basis, we put, in the normal polar coordinate system or spherical coordinate systems, the basis vectors point along the curves of constant. One of the coordinates is constant. You point along the curve. So that's the same. What's not the same is that in a polar coordinate system or spherical coordinate system, the basis vectors are chosen to be unit magnitude. And that puts the complexity in the coordinate, in the components, rather than in the basis vectors. With a coordinate basis, you're doing just the opposite. The components are very simple. They are simply, for a displacement vector, they're simply the change in the coordinate value. and all the complexity is put in the basis vectors. They're changing in magnitude as you go from place to place. So you can certainly invent a polar coordinate basis, but it's not the same thing as polar coordinates that you're familiar with. You understand what I'm saying? Okay. So I've got an exercise for you to spend a couple minutes on here. So we're going to consider theta and phi coordinates on the surface of a sphere of radius r, where curves of constant theta and constant phis are lines of latitude and longitude respectively. But we're going to assume that theta equals 0 at the North Pole the way we do in physics as opposed to the way we do it on the Earth's surface. So the curves are perpendicular everywhere except at the poles where the coordinate system breaks down. And so by considering the formula between infinitesimally separated points, you know how to do this. Calculate what's the formula for this and then figure out what the metric must be. All right? So, have at it. Work at that a little bit. See if you can figure out what the metric for spherical coordinates. Yes. Yeah. Yeah. That's right. Yeah. 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 Yeah, it'll work. But you can, I think you can visualize it more geometrically the way. Uh-huh. Huh? Uh, how you coming here? Huh? So let's let's think about this a little bit together. So if what I want to do is find the length of this tiny displacement on the surface of the globe, and if I can treat this little area as if it were a flat space, because my displacement is so small, then all I have to do is find out what this length is and what this length is and take the sum of the squares of those lengths. And how do I know that well, let me ask this question. Are there off-diagonal components to this metric? No, because why? How do you know? Yes, because the perpendicular. The basis vectors for spherical coordinates are always perpendicular. The curves meet at right angles everywhere on the surface of the globe. So that means that dot product between the two basis vectors is 0. So no off-diagonal components. So all I have to do is worry about what's this length, take the sum of the squares. So let's do the easy one first. What's this length? I've drawn it a side view here. I'm doing a little change in angle. What's the length of that segment? Yeah, this is going to be r times d theta, right? Okay, that's the easy one. Now think about this length. Okay, what's that going to be? Yeah, r sine theta, right? Like that. Does that make sense? And why is it sine theta? I'm thinking about a circle, this circle that I'm looking at end on here, and I'm asking, well, what's the radius of that circle? Well, the radius is actually is the if this is r, then this is r sine theta, and so the radius that I want to use for figuring out the length of that arc is r sine theta. So what do we got here then? This is what? R squared. This is r squared sine squared theta. So the metric is, if I write it as a matrix, it's going to be r squared 0, 0, r squared sine squared theta. Good? Is that? And that might look familiar if you know the Schwarzschild coordinate system. That's just the angular part of the Schwarzschild coordinate system also. Okay, great. So let's continue. So we're going to try and figure out how to do tensors in this coordinate basis. So for the moment, we're going to go back to considering a two-dimensional, possibly curved surface in space, and I'm going to consider a general coordinate transformation from UW coordinates to PQ coordinates. Okay? And the chain rule for partial derivatives means that if I want to find out the total change in P, then I got to figure out how much P changes with U times du times the partial of P with respect to W times W, and the same sort of thing for Q coordinates. And if you want to write that abstractly in index form, it looks like this. So that's a transformation of the displacement vector. The components of the displacement vector is given by this transformation law. So just like we did in special relativity, we're going to make that the transformation law for the components of a 4 vector. That's going to be the definition of the transformation law for the components of a 4 vector. And this just generalizes what we did before, because if you think about it, these partial derivatives, if you were to take the Lorentz transformation equation and take all those partial derivatives of x prime as a function of t and x and y and z, you get the components of the Lorentz transformation. So this is a generalization of that idea. And there is this important identity, which is basically that if I take the derivative of the prime coordinate system with respect to the unprime coordinate system and then multiply it by the partial derivative the other way around, I get the identity matrix, which is basically saying that these transformations are inverses of each other. And you can see how that works out in our two-dimensional space. If I take this expression and write out what that sum over nu is, it just becomes this. But that's the definition of dp over dp, which had better be 1. And similarly, if I write it out here, I'm getting the derivative of p with respect to q, which had better be 0, and so on. So this is just writing out what that abstract relationship says. And so I'm going to do a general tensor transformation law. I'm simply going to make do the kind, so these behave almost exactly like the Lorentz transformation and the inverse Lorentz transformation. And so I'm going to simply define a general tensor to be just like we did for Lorentz transformations. You use a direct transformation for every upper index and an inverse transformation for every lower index, as many indices as you've got. And that way, everything will transform alike. It's just the way we've done it before. Okay, so, and in particular, we can show, for example, that the metric tensor really is a tensor. It obeys this transformation law. And the way to do it, and the reason I'm working it out in full is because the metric tensor is a really important tensor, but also because it illustrates a concept that for doing these kinds of logical proofs that I want to make really clear. So I'm writing down here, what am I saying here? Yeah, the space-time separation or just distance in ordinary space is coordinate independent. Okay, what did I do here? Yeah, I transform the displacement coefficients, okay? So, but I should have a prime here. It's like down here, okay? And so what did I do here? Yeah, I just rearranged terms. I don't have, I can associate any way that I want. I wanted to pull these things out in front. Okay, now what did I do here? Yeah, I changed the names of the variables. I've got bound indices here and here. I can call them anything I like. Okay, so I'm going to call them mu and nu, whatever. And what did I do here then? Yeah, so I pulled the left-hand side, and the reason I renamed the indices is so I could pull those things out as common factors. All right? And so this has got to be 0. Now, why can't I just divide both sides by dx super mu, dx prime super mu, dx prime super nu? Why can't I just divide those out and say this? This is the importance. Yeah, that's right. And to express the same idea in a different way, this is a sum. And just because a sum is 0 doesn't mean that each individual term in that sum is 0. So, but I definitely want to go here so that I can get here, which is the tensor transformation law for the metric tensor. So how am I going to do that? Yeah. Uh-huh. Uh-huh. Yes. Okay. Yeah, that's one way. That is one way of doing it. And let me give you a different way of doing it, which also expresses, I think, the same idea in essence. This has got to be true for arbitrary displacements, right? Which means I get to choose whatever displacement I like, and it's still got to be true. So, for example, let me choose these things to be purely in the p direction, say. Okay, so there's no q component. So this becomes just dp, and these become mu and nu become p and so on. So I'm picking out one term out of the 4 terms that I have in 2-dimensional space, and I'm saying I can choose the displacement to be in the p direction purely, and then I know that that pp component is 0. Okay? Or I could choose it purely to be in the q direction. And And then I can show that the QQ component is 0. And then I could work by doing combinations of appropriate things. I can nail down all the other components similarly. So the fact that I can choose this displacement arbitrarily means if this is true, then this is true because of all the possibilities I could nail down every single component. Does that make sense? Any questions about that? So that's the kind of proofs that you can do with this. Okay? So let's see what's next. So we can, other tensors and tensor operations you can prove in a similar way. So the Kronecker delta remains a tensor even in this arbitrary coordinate systems. You can prove that in a similar way. We can define the inverse metric with the upstairs indices so that it yields the Kronecker delta. And if this is a tensor and this is a tensor, then this is a tensor with two upper indices. I can lower an index. I can raise an index. And the quantities transform alike. And the proofs look just like they did in the flat space-time situation, Lorentz transformation. So we can put together all these, and so all the tensor operations work and everything. Everything that we did before still works. But I want to emphasize that this only works in a coordinate basis, where the components are really simple this way. And more complicated bases would require much more complicated math. So we stick to coordinate bases basically to make the things easier. So, and you can show that the gradient of a scalar field transforms like a covector, a one form. And that all works fine. But the gradient of a vector is not a tensor. And that's a problem. So if I take the gradient of a 4-vector here and look at the transformation law of that, and actually I should have a prime here and a prime here so that I'm completely consistent. So I'm transforming into the prime coordinate system, and I'm just doing the usual kind of partial differential calculus there. In this particular case, I'm transforming back the way I did up here using chain rule. And I get two terms. Now this term looks right. That's what the tensor transformation law ought to be. But this term is extra. Can you see that? And that's a problem. Now, why didn't that arise when we were considering Lorentz transformations? Yeah, we're looking at this. I'm taking the double derivative of the transformation components, but in Lorentz transformation, those components of the transformation were constant, so no double derivative. But you can't say that for sure in a curvilinear coordinate system in a curved spacetime. Okay, so we got to worry about that. So I'm going to, but before we get to worrying about that, I want to think of a little bit about a parabolic coordinate system. So here's a coordinate system for a flat space-time. And it's basically, I'm using as the curves of constant p, they're just straight lines the way they would be in the Cartesian coordinate system. But curves of constant q are parabolas like this. So that's a mapping of a flat space, two-dimensional space onto curved coordinate system. And so if I've got basis vectors, you can see that the basis vectors are not orthogonal. And if I have an A vector, I can talk about components in the background Cartesian coordinate system, but they'll be different than they would be in the parabolic coordinate system. So let's think about this. So we're kind of running short on time, so I'm going to skip over some of the things here, but let's see. So if I've got P is equal to X, and I've got Q is equal to Y minus CX squared, how could I invert those? What is X as a function of P and Q? Yeah, X is P, that's easy. What about Q? Well, I want to solve, or Y, I want to solve for Y, so Y is equal to what? Yeah, C, and I would say, looking at this, CX squared, but I want to express it in terms of P, so it'll be CP squared. So there's the inverse transformation. If you do the partial derivatives, you get partial of P with respect to X is equal to what? Partial of P with respect to X. 1. Partial of P with respect to Y. 0. Partial of P with respect to X. I'm sorry, partial of Q with respect to X. Yeah, minus 2CX. Partial of Q with respect to Y. Yep. Equal 1. And we can do the others. Partial of X with respect to P is 1. Partial of X with respect to Q is 0. Partial of Y with respect to P is 2CP, and partial of Y with respect to Q is 1. Yes. Okay, so there are all the partial derivatives. So if I wanted to find tensor, the metric tensor components, what would I do here? So say I want to find GPP. That would be, I've got to take a partial for each thing. So I've got an X mu over P, an X nu over P times G mu nu, right? Where this is the background Cartesian coordinate system. So in fact, I'm transforming from the Cartesian coordinate system to the PQ coordinate system. And what would that be? Well, it's going to be X dp dx squared times gxx, right? Plus dy squared dp equal times gyy plus what? Why no others? Yeah, Cartesian coordinates gxy and gyx are 0. So these are the only two I need. Well, what's this? Looking here, I'm looking at this. So that's 1 times 1. And then the dy dp is 2cp, so 4c squared p squared. Okay, that's the GPP component. And you do the other ones analogously. Okay, So how would I, in fact, so let's imagine, I'm going to erase this line. So let's imagine that I want to, I have a vector with components AP is equal to 1, AQ is equal to 0. So this is a vector that's a unit along the P direction. And what would its x and y components be? Ax, ay is equal to, well, I take the partial with respect to x with p times ap plus the partial of x with respect to q times aq, which is what? Well, I've got this is 1 times that is 1. So 1, and then this dx dq is 0, so forget it. That's the component there. Ay is going to be the same thing. Pax plus dy dp ay. Okay. Well, I'm sorry, I got it wrong. Yeah, sorry, p and q. PQ. Okay, so y dy dp is 2cp times 1. This is still 0, so this becomes 2cp. Okay, so this vector, which looks constant, is actually in the xy coordinate system. It's got a y component that depends on p. Does that make sense? We'll go back and look at the coordinate system. So here's my vector. It's tangent because right here the basis vector in the p direction is tangent to this curve. This vector is going to be tangent to the curve. And you can see that in an xy coordinate system, as I get farther away from 0, I'm going to get more and more of a y component. It's because the basis vectors are changing. So even though this looks like a constant vector field, it's not, because the basis vectors are changing. Does that make sense? On the other hand, if you work out what the magnitude of this is using the metric, so if I take in the Cartesian coordinate system, it's easy. If I take the square of this plus the square of this, I get 1 plus 4cp c squared p squared. And if I did it in the PQ coordinate system, I've only got a p component. So if I evaluate what it is, it's just the value of this squared times the GPP component, which will be the same thing because we've calculated. So the magnitude of the vector is the same, which it better be, right? Because the magnitude is supposed to be frame independent. Okay, great. So, how are we going to deal with the gradient problem? This is what we're going to talk about next. So I'm going to define things called Christoffel symbols, and I'm going to define them this way. So I'm going to take a little displacement, and I'm thinking about mu as having a certain value here. So say mu equals p. I'm going to take a certain displacement in the p direction, and I'm going to ask, how much do the basis vectors change? Say the p or the q basis vector, how much does it change? And then I'm going to write that as a vector, so it's going to depend on which direction I'm going in and which basis vector I'm talking about. And then I'm going to expand this. The vector, this is going to be a vector ultimately, a little displacement. And I'm going to say that I can expand that in terms of the basis vectors because it's a vector. So this is these coefficients then are the Christoffel symbols, and they describe basically how the basis vectors are changing. Now, in a Cartesian coordinate system, what would these Christoffel symbols be? 0, all of them, because the basis vectors don't change in direction or magnitude as you go from place to place, right? So if you think about it, then the physical change in the vector. So I'm saying now I'm going to walk a little distance, and what I'm going to ask, what's the change in the basis in this vector, the true change, imagined by calculating it in the background two-dimensional flat space that we're thinking in the background. And I'm just going to, what did I do here? So I wrote what that definition of that vector is in the coordinate basis. And what did I do here? Yeah, it's basic chain rule and product rule, right? So I'm applying the product rule. I take the derivative of this and hold this constant, and then I take the derivative of this, and so. But I do have to think about. I'm taking. So this is basically the change in the components, holding the basis vector constant. And this is the change in the basis vector holding the components constant. So it's just product rule of calculus. But this thing, according to that, I could replace the partial derivative here with the Christoffel symbol, and I can rename the sum here. I'm going to rename it alpha and alpha so that I can pull out that this dx alpha. And I'm going to group the terms together. I get that. And then these are components of a change. I mean, these are components of this vector. But since the components are being expanded in the usual way, this must be a tensor, which I'm multiplying times another tensor to get what amounts to components of a 4 vector. Okay? So I'm going to call that combination thing. This combination thing is a tensor. And that's what we really want. We want an expression that reduces to the ordinary gradient when you're in a Cartesian coordinate system, but nonetheless works in any coordinate system. And so these terms basically correct this. Testing. All right. Right. So you can see how the point that I'm trying to make is that this gradient would be fine as long as the basis vectors would stay in place and not change in direction or magnitude. This corrects for the changing in magnitude so that the combination gives you the actual change in the vector as you would compute it in your background flat space-time. And so this gives you what you need. So the tensor gradient of a scalar is the same thing as the ordinary gradient. We can use that to figure out how we find the tensor transformation for a one form, and in light of time I think I'm just going to basically skip over that. But what happens is that you end up with subtracting the Christoffel symbol instead of adding it. But otherwise it looks like pretty much what you need. Okay, and so for a general tensor transformation, if you're going to take a, I'm sorry, if you're going to take a gradient of a general tensor, you take the partial derivative of the tensor, and then you correct each index in turn for the changes in the basis vectors. Because each component, each index involves projecting on the basis vector, and the basis vector is changing, so you need to do a correction for that. All right? So that is that. So great. The trouble is we'd like to be able to calculate those Christoffel symbols. And I'm going to assume, you can assume that the Christoffel symbols are symmetric in the lower two indices. That is not at all obvious from the definition of the Christoffel symbol, that they should be symmetric. And in fact, it's not actually mathematically required. So in general relativity, we're going to assume, however, that space-time is torsion-free, and that's what that symmetry means. It's an extra statement. And it's kind of a hidden assumption of general relativity. It turns out that a lot of manifolds that you would think of as being curved manifolds, particularly manifolds that you can embed in a larger dimensional space, Euclidean space-time, are going to obey this. So it fits one's intuition about the way a curved space-time ought to behave, but there is no mathematical requirement, and people have actually poked at this to try and see what non-torsion-free space-times might look like. But it's fair to say that any space-time that has torsion is not a general relativity space-time. You're talking about a different theory. Okay, so we're going to assume that, and then it turns out that you can prove what the Christoffel symbols are in terms of the basis by basically taking, remember that the metric is a dot product of the basis vectors, and you just apply the definition of the Christoffel symbol. You essentially take a derivative of that dot product and unpack it and use this symmetry, and you get this. And the easy way to remember this is that the bottom two indices here are the same as the indices here in this negative term, and then the others you just get by rotation of the indices. So here is the same set of indices, except I've rotated the mu to the front, and I've got the sigma and the mu rotated back, and similarly here I do another rotation. I move the mu to the front, and so on. Okay, so that's the way you can memorize that. So if you're on a desert island somewhere and you need to know the Christoffel symbols, you're set. Okay? That's right. Yeah, it's only true in a coordinate basis. Yes, and it's one of the reasons that we want to use a coordinate basis is it becomes much more horrible if you're not in a coordinate basis. There are many other terms here, so it's harder to calculate. All right, so let's see. So here's an exercise we can do to determine the tensor gradient in the parabolic coordinate system we were working with. And actually, I think I'm going to skip over that exercise. There's a lot of work there and time is short, but let's do the last part of it. So let's assume that all the rest of it works. First of all, so I've got hx equal 1 and hy equals 0. So let's do part A anyway. So I'm still working in this parabolic coordinate system, and here I've got a different, this is a truly constant vector field in the background flat space, right? And so what I want to do is find HP, which is partial of p with respect to x times hx, and hy is 0, so this is it, and this is just 1 then, right? So what about HQ? It's partial of q with respect to x times hx, which is 1, and partial of q with respect to x minus 2cx. Okay, so that tensor field doesn't look constant. Okay, but let's find out what its components are. And in particular, it looks like we're going to have, I'm sorry, and I should say this is HQX, but let's express that in terms of p coordinate. Okay, so let me calculate one component of this. Let's say the p derivative, that's going to be the interesting derivative. So I want p of the HP component. So what would that be? I'm going to take the ordinary derivative of HP, and then I'm going to say the Christoffel symbol for p, and the only component of and then I'm going to take the p derivative, and then I've got mu here times h mu in the PQ coordinate system, but it's only got, well, it's got two components here, right? So I've got HPP times HP plus Christoffel symbol P, PQ, HQ, right? So what's this? 0. What's this? Well, I've got a list of the Christoffel symbols, and it turns out, gee, there's only one Christoffel symbol that's not 0 in this case. And that, which actually makes sense because only one of those basis vectors is changing direction. It's the p basis vector that's changing direction. Did I get that right? No, it's q basis vector. No, it's the p basis vector that's changing direction. And yes, and it only changes in the q direction when it's moving. So that's 0, and this is 0. So 0. Okay, so let's do, so HP is not interesting. Let's do the derivative with respect to Q. So now I've got a derivative of HQ with respect to P, and that is not 0. And then I've got Q, PP, and times H, I'm sorry, yes, P. And then I've got some other terms here, but this is the only non-zero term. Okay, so what's that? I'm sorry, I'm going to erase this. I think we're done with it. So what is this derivative? It's minus 2c, right? Because I'm taking the derivative. And what's this? I said that was 2c. What's HP? Yeah, plus 1. So what do I get? Okay. Should I get 0? Yes, the whole point of this is that we're trying to evaluate whether this vector field is changing or not. And we know that it's not changing in the flat space coordinate background. And so it better not, if it's going to be a tensor, it better not change in my PQ coordinate system. In other words, this tensor gradient should evaluate that way. So you see how this works? All right. Yeah. Exactly. And it's 0 and none. I don't need to do any other work. I'm assured that it's going to work out that way in any coordinate system. Well, if it's 0. And it is true that if it's not 0, it will be different values in different coordinate systems, but it will be a transformation, an ordinary tensor transformation of whatever the value was in Cartesian coordinates. You just transform that value as a tensor into your new coordinate system, and it's fine. So the point, though, is that this absolute gradient is the tensor gradient is a tensor, and so you can use it in equations that are going to work in every single reference frame then, and that is the beauty and the power of it. No, not particularly. I like the tensor gradient because it's a gradient and it's a tensor. Uh, and covariant derivative is a little more ambiguous in that particular regard. Okay? So let's talk about a geodesic equation then a little bit. So a geodesic is, the way I've defined it and want to talk about it, is locally straight. And what do I mean by that? Well, I sort of mean a very practical kind of thing. It's the straightest path you can choose, which means that the direction of something's forward velocity is not changing in your local flat coordinate system. So if I wanted to construct a geodesic, one way you can imagine doing it is say you want to construct a geodesic on the surface of the Earth, lay down a city-size map on some place in the surface of the Earth, draw a straight line on that map, and then move to the end of that straight line, set down another city-size coordinate system, draw a straight line on that, and a straight line on that, and so on, and keep on going, and eventually your path will become a great circle. But the idea is that at each local step along the way, it is a straight line, and so you're going to be assured it's the straightest possible line that you can draw. So let's imagine doing that. So I'm going to say that the derivative of the forward velocity with respect to the object's own proper time is going to remain a constant in the local flat coordinate system. Yes?
Right there,
Yep.
can't we start there by thinking like physicists and less like experts on geometry?
Yeah, yeah. No, zero acceleration is what we're saying. Yes, absolutely. Same idea. Yeah, yeah, thank you. That's true. So zero acceleration. So I'm going to expand what that means. The trouble is my basis vectors are changing too, and as the particle moves, the basis vectors are changing around under the particle, and I've got to include then the rate of change of the basis vectors along with the rate of change of the components if I'm going to get a true sense of how the particle is actually accelerating or not accelerating. Okay? So what did I do here then? Well, the derivative of u component with respect to t is just that. What's going on here? What did I do? Where did this come from? Yeah, that's just the forward velocity written in terms of position. What's this? What am I doing here? Yeah, chain rule. The fact is that the basis vectors are changing with proper time only because the particle is moving, changing position. The basis vectors depend on position, so I'm using the chain rule there to expand what that is. Okay? And then what did I do as I went here? Yeah, I used the definition of the Christoffel symbol to replace this. Okay, what did I do as I'm going here? Yes, I renamed the indexes mu nu to alpha beta so that I could actually, let me think here, what did I? Yeah. Yeah. Oh, that's right. Yes, I basically I wanted to pull out the alpha sub mu, but in order to do that, I was using mu, so I need to change this name and that name too. So I was able to pull out a common factor. And the point of that is that then this is a 4 vector. This is a component of a 4 vector because it's multiplied times the basis vector. So that's the definition of the component of a 4 vector. So the geodesic equation is, we're saying that the total rate of change, that's really sort of 4 component equations, and we now have got those 4 component equations. All of those are 0. So there's the geodesic equation, just by the idea that it's locally straight. Okay? So let's look at how this works in our horrible PQ coordinate system. So here's my geodesic equation. I'm saying let's evaluate the P and Q coordinates of that. So geodesic equation says the double derivative with respect of P with respect to, if we're working in a two-dimensional space, it's just distance that we're using as the parameter. And I'm then saying plus P mu nu times all the possible 4 velocities. But I'm sorry, this is S. Okay? So what is that? What's this? 0, yeah. There aren't any Christoffel symbols. So I get just that the double derivative is equal to 0. So what's the solution? P is equal to AS plus a constant. Let's define that constant to be 0, meaning that the P coordinate of our particle at S equals 0 is going to be 0. All right? So great. Now let's do the other one. Double derivative with respect to Q of is plus. Now I've got one of these is non-zero, the QPP dP ds dP ds plus zeros. Okay? So what's this? This was 2C. What are these? Yeah. Okay, so the equation is double derivative of Q with respect to S is equal to 2CA squared. Right? Yes, minus. Thank you. Okay, so what's the solution then? So I undo, well, this is a constant. We know how to do this, right? So Q is equal to CA squared S squared, right? Plus some other constant, let's call it B times S, right? Plus some other constant, let's call it Q0 because it'll be the value of Q when S is 0. Okay? Great. So what have we learned? Well, let's think about going back to the PQ coordinate system, or the XY coordinate system. So I had x is equal to, and I've got this written down, I think. Do I have it written down up there? Yeah. So x is equal to p, and q is equal to, I'm sorry, and y is equal to cp squared y plus q, right? So, great. So what's x then? In terms of s. S, all right? What is y? Well, y is going to be c times as squared, so c squared as squared, okay? And then plus q, but q is equal to this, which is minus ca squared s squared plus bs plus qo. What happens? Sorry, minus. Thank you. No, I was right. Yeah, these cancel out. I got, and if I think if I could, I'm going to get rid of s now, so I'm going to solve this expression. S is equal to x over a. I'm going to plug that in here. So I got that y is equal to b over a x plus q0. What's that tell you? Yeah, it's the equation of a straight line. Okay? So what I'm showing is that in this strange PQ coordinate system, we apply the geodesic equation, we get straight lines, which is what we wanted to get. So yes, we're golden. All right? So let's think a little bit about, I think what I'm going to do is skip over the Schwarzschild thing and go to talking about locally orthonormal and locally inertial frames. And then if we have a little time left, I'll come back to the Schwarzschild thing. But what I was going to do, let me summarize briefly what and you can look at it on the online. By the way, I put a new version online that corrected a bunch of errors and also shortened. It's still not quite short enough. But if you downloaded or printed the previous version of this lecture, you should download the new lecture, which fixed some of the errors. But what I was going to do with that is take the Schwarzschild metric and apply the geodesic equation and show that for a particle at rest in a Schwarzschild space-time, the geodesic equation delivers you what you'd expect, that the acceleration of the particle would be exactly what you'd expect from Newtonian gravity. Yes, except there are some subtleties to that, which you were about to mention. Uh-huh. Yeah, Kirchhoff symbols. Uh-huh. Yeah. Yes. Yeah. Right. Uh-huh. Yeah. Yep. Yes, that's right. 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 Uh-huh. 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 Yeah. You're right. Yes. Right. Uh-huh. Yes. Uh-huh. Right. Correct. Yeah. And that's what. Yes, that's right. Yeah. Uh-huh. Right. Right. Yeah. So there is actually some theoretical richness to explore with that idea, and I was partly trying to emphasize that yes, there are unexplored directions here that are worth thinking about, and that Einstein and what you're adding is that Einstein himself explored that, and other people have explored that too. And this is an interesting idea, but the reason I'm not delving into that is because it's not general relativity, not the theory of general relativity as we have it presented. But there are some really interesting things to explore there. But anyway, that you can look over that section. It's not very long or complicated. It just shows you how to apply the geodesic equation in a realistic situation like that, and you get the answer you'd expect from Newtonian gravity, which is pretty awesome. All right, so Schwarzschild metric initially at rest, blah blah blah. Okay, so I want to talk a little bit about the local flatness theorem because this is going to be important for us as we go on. And so the local flatness theorem says that at any given event in spacetime, our freedom to choose coordinates allows us to construct a coordinate system, first of all, where the metric is equal to the flat space metric. Secondly, and you still have 6 degrees of freedom left over, which correspond to boosts and rotations. Okay? And you can set all 40 of the independent values of the derivatives of the metric to 0. And why are there 40 of those values? And not, shouldn't there, shouldn't there be 64? Yeah, the metric is automatically symmetric. So there are only 10 components of the metric that are independent, the 4 diagonal components and half of the 12 remaining components. And so you have 10 components of the metric, and there are 40 derivatives of those, and you can set them all to 0. Your coordinate freedom allows that. But what your coordinate freedom does not allow is to set all the double derivatives of the metric to 0. You can set 80 of them equal to 0, but there are 100 of them. And no matter what you do with coordinates, you got 20 double derivatives of the metric left, 20 independent values of the double derivatives left that you cannot set to 0. Now, the proof of this is complicated, and it's even hard to give an idea of an overview. If you're really interested, you can look at my textbook where I have a couple of pages that goes over the discussion of this. But it is a really important theorem, and partly because what we do physics in is frames like this. We want to use a Cartesian-like coordinate system. And so if we were going to do physics in this room, we'd set up orthogonal vectors, and we'd synchronize our clocks, which we can do locally, as long as we don't do too high or too low in the gravitational field. and we do all the normal things that we do to set up things, and then we do our measurements in that coordinate system. And what this theorem is saying is, yeah, you can always do that. You can always set up the metric to be the flat space-time metric. And if you do that, then what you've got is a locally orthogonal coordinate system. And that is satisfying the first. But if I'm not in a coordinate system where I also satisfy the second criterion, then I'm in a coordinate system like the surface of the Earth, where, let's see, something I can throw that won't break. Okay. In the coordinate system of the Earth, yeah, my coordinates are orthogonal. I can set up my Cartesian coordinate system, but my Christoffel symbols, which depend on the first derivatives in the metric, they're not zero, all of them. So if I take a particle and release it, it falls. And the acceleration's not zero. So what would be a kind of a coordinate system near the surface of the Earth where you have all the first derivatives in the metric zero? What would be that kind of a coordinate system? Yeah, freely falling reference frame, like International Space Station or something like that, or God forbid a falling elevator. Okay? So in such a frame, those are the kinds of frames where all the Christoffel symbols are zero, your particles don't accelerate, they move in straight lines at constant velocities. That's a locally inertial frame. And all of these things are true only at a point, strictly true only at a point. So you get very far away from that point and you start to notice discrepancies, which are the tidal forces and so on. But at a point, you can always make these coordinate choices. And that's a very, very important idea. Because, like I say, we do our work in locally orthogonal frames most of the time, and locally inertial frames if we're lucky enough to fly in space. Okay? So, and what I'm going to show you very briefly here is a trick for converting from an arbitrary coordinate system to one of these coordinate systems. Now, if we really knew, I could use the ordinary coordinate transformation rule if I knew how to map my coordinate system components onto a global coordinate system. But usually I don't know how to do that. I don't have expressions, but I can still do it. Let's assume that we know the basis vectors of a locally orthogonal frame. And I'm going to assume that that's the prime frame. Then I know that the components are this, and here's my metric. So if I take the dot product of one of the basis vectors with my 4 vector, then this becomes the metric, which just lowers, gives you the prime, the prime frame. So in my locally inertial frame, it gives you the one component there associated with whatever basis vector you're using. Now, I'd like to raise that. And since I know that in my locally orthogonal frame, my metric is just the flat space metric, I just take that dot product, whatever it is, and raise the index, and I've got the upstairs component of that, which is the normal 4 component. Okay? And so you can evaluate the components of the vector A in a locally inertial frame. That's what we're doing here. As long as I can evaluate this dot product. Okay? But the beauty is, you can the dot product has a frame independent, coordinate system independent value. So you can evaluate that dot product in any coordinate system you like. And in particular, for example, if you are working in this room and you wanted, here's a particle streaking through, it has a certain kind of form momentum. You want to figure out what the components of the form momentum are. If I can find an expression for the components of the basis vector in a Schwarzschild coordinate system, which applies everywhere, not just locally, applies everywhere, and I can find the form momentum components in that Schwarzschild coordinate system, I can evaluate the dot product in the coordinate system, and then I've got what the form momentum is in my own private reference frame. So this turns out to be a really powerful technique. And so we could do this in Schwarzschild coordinates, and I had an example here, and I'd invite you to read that in the handout. And I'm sorry I don't have time to go over it now, but the point is that this is an extremely powerful technique for being able to evaluate physical things that you would like to measure in a given reference frame. And the example that I do in the sheet is looking at a falling particle that's falling in Schwarzschild spacetime from infinity and asking what's its velocity to a person that's sitting at rest watching the particle go by. And the way you do that is take its forward velocity, you evaluate its components in the locally orthogonal frame of the person sitting at rest. You've got ut and ux, and x over ut gives you the ordinary velocity, and you just calculate it. It turns out that that ordinary velocity for a particle falling at rest, I think I've got it on this screen here. So you do a whole bunch of calculations. So there are the components of all my relevant vectors in the Schwarzschild space-time, and you calculate it, and you get this. This is the falling velocity. Okay? And where does that falling velocity reach the value of 1? Yeah, at the event horizon of the Schwarzschild black hole. So what we're saying is that one of the characteristics of the event horizon of a black hole is that an object falling at rest from infinity will reach the speed of light. And this, as measured by the local person who's sitting there near the event horizon watching it drop past. Okay? And that's actually an interesting result, which is not at all obvious. And so your escape velocity, to reverse it, to go to infinity, your escape velocity has to be speed of light if you're going from the event horizon, which is why you're not going to escape. Okay? So, like I say, this is a very powerful method for figuring out these quantities in locally orthogonal frames, the kind of frames that physicists actually use. And when I talk about the Schwarzschild metric next section, we'll talk about why it's sort of hard to use that frame. It's hard to interpret in a lot of cases, and this provides a very powerful interpretive tool that I think everybody who does general relativity ought to know more about. It's not really out there in the literature very much, so it's good to know. Okay? Good. So I think I'll quit at this point, and sorry, still going over, but I'll be around here, between the sessions and also after lunch in that seminar room if you want to talk some more. Thank you all for your attention.